So thank you for joining us. So now 3 participants here. So may I ask you to open your video?
Yes,
Hi.
Bunsho.
Hi. Hi.
Hello.
Hi.
Hello.
And Dr. Juan. Dr. Juan, where are you?
He is with me. He is with me.
Okay. All right. So which university?
Central China Normal University.
Okay. Right. So then please understand that this meeting is now recording. So later that is open for everybody to see the detail of our newly developed method. So please understand this, okay?
Okay.
So then I will explain you briefly our technique, and then I will accept your question if you have, right?
Okay.
So then I will start this here. There are the many analytical methods for solid materials. And if they are categorized by using 2 axes, the one is a surface bulk and the macroscopic and the microscopic. As you know, the XRD is a very, very powerful technique of characterization of crystalline material. And that is macroscopic. So we can totally analyze the crystalline composition of material in solid materials. However, that is limited to crystalline phases, and no amorphous phases can be detected and characterized. And for the surface analysis, there are a lot of surface analysis, but almost all the surface analysis techniques are categorized into microscopic. So we can know the detailed structure of surfaces by using TM, STM, AFM, or something. However, they are just microscopic. So therefore, only we can see the part, only the part of materials, and that is easily observed part is chosen for analysis. And but there is no guarantee the other part has the same structure, and probably the many type of surfaces are there, and there are a lot of how to say, and there are a wide distribution of those different surface structures. So therefore, it is necessary to see the macroscopic image of surfaces, but almost no technique. And only limited analytical method, electrochemical impedance, data potential, temperature program desorption shows the macroscopic information of surface structure. However, the target of those measurement techniques are limited. Only the part of solid materials can be analyzed by using this. In ordinary powders, it is a bit difficult to obtain the macroscopic information of surface. And also, as I told you in the beginning, XRD shows only the crystalline structure, and we have no technique to characterize amorphous. The RDB-PAS, our newly developed technique, is just a macroscopic surface analysis, and also are sensitive to amorphous structure. The principle is very simple. Sorry. Very simple. We assume the presence of vacant electronic states that is called electron trap. They probably are in the band gap, among the band gap of semiconducting material or insulators. And the principle is very simple. By exciting the electrons in valence band directly into electron trap to remain in those electron traps. And the filling of vacant electron trap gives new photoabsorption. And this absorption, for example, the titanium oxide case, if titanium oxide, the titania is reduced, they are colored to be gray or bluish gray. So that is the reduction, that is electron accumulation in material. And those new absorption, photoabsorption is detected by using PAS, photoacoustic spectroscopy. Photoacoustic spectroscopy is itself is a conventional analytical method enabling to detect the small photoabsorption by using sound. So the photoabsorption of modulated light gives the sound from the material. So because of the photoirradiation and the photoabsorption gives the heat, and that is modulated. That means the expansion shrinkage is repeated. So that gives the sound. So we can detect the sound of frequency, same as the modulation. So therefore, we can see, we can observe the change of photoabsorption by microphone. And there is no other optical one. So therefore, it is possible to detect the accumulation of electron in electron traps by scanning the continuous light from lower energy side to higher energy side. So that means the first, the deep and low energy electron traps are filled. And then this is accumulation is proceed to fill up all the higher energy electron traps. This is the setup. This is the cell, the main part of cell with the microphone here. And sorry, I will microphone here. And two light beams are introduced. One is the excitation light, one is the detection light, and that is combined into one beam to be introduced into reaction cell, measurement cell. And this is a sample folder, and like XRD, the dip, there the dip, and powder is, if powder is measured, this is filled, and O-ring gives the sealing in a photoacoustic cell. And normally the powder, the minimum 100 milligram, and of course it is one measurement without checking the reproducibility. 50 milligram is okay, but normally we accept the powder sample with the weight of more than 300 milligram. That is preferable. For the film on the substrate, the size 12 millimeter square, that is just inside this O-ring. So therefore, is preferable, or larger size substrate, glass substrate is preferable. We can cut off to be used in this cell. So if you want to measure your sample, in the powder form, about 100 or 300 milligram, and the film something like this. And the thickness, required thickness depends on the substrate and of course the sample itself. And preferably the thick film, about thicker than 500 nanometer, or preferably 1 micrometer thickness. That is very easy to detect. But if that is the thinner, we try to check, but actually the thicker, the better to be detected. The measurement system is something like this. This left top panel shows the actual photoacoustic signal change by scanning the wavelengths from longer wavelength side to shorter wavelength side. And this shows the accumulation of electron traps in electron traps. And here, the small increase, and here is a large increase. And this is differentiated from the lower energy side to higher energy side to give the energy distribution of electron traps. However, this is the relative value. So we introduced the calibration coefficient by using the chemical titration technique in the literature. And this is converted into absolute density of electron trap at each energy from valence band top energy. The reference is valence band top energy. And using the same apparatus, we can observe the photoabsorption, something like a diffuse reflectance spectrum. The band gap is calculated by the absorption edge wavelengths, and the band gap is the difference between conduction band bottom minimum and the valence band top. Therefore, the conduction band bottom position can be plotted in the same figure as a difference to valence band top position. And this is the ERDT, energy reserved distribution of electron traps. And this dotted line is CBB, conduction band bottom position. And the number figured in this parenthesis is the total density of electron traps. And this is the example, and this is the commercial titania with code name STF4, this specific surface area, and annotates with small amount of rutile. However, without knowing this code name, specific surface area, and the crystalline structure, we can identify this titania as STG4. And this is a representative titanium samples. And later I will show the other metal oxide. And the annotates, as you know, annotates rutile brookite is the generally obtained crystalline structure. And the annotates with small amount of rutile with small amount of annotates. And the ERDT pattern, the CBB and TD depend strongly on each sample, but it seems that the ERDT and the CBB position depends on crystalline structure, bulk crystalline structure. The important point is the amorphous. Previously we can obtain the amorphous, commercial amorphous titania, and this also gives the similar ERDT CBB pattern. And that is not only crystalline, but also the amorphous phases are detected. And of course, the ERDT pattern strongly depends on the crystalline type or amorphous, but not only bulk structure, but also surface structure is reflected in this pattern because the total density of electron traps are almost proportional to specific surface area. It is a bit difficult to say almost, but the tendency is clear. So therefore, almost all the electron traps are located on the surface with a similar density, 1 electron trap per square nanometer. As you know, for titania, surface hydroxyl group, the density of those hydroxyl group is about 2 or 3 per square nanometer. And this ET density is similar to those density. And another important point is from this slope gives say that the electron traps are not something like point defects that might be governed by the surface reconstruction structure. So anyway, the surface, the electron traps are located mainly on the surface, and therefore the pattern, ERDT pattern, depends strongly on the surface structure. This here, the all anatase, of course, there is some amorphous, but anatase samples, this right one and left one, the similar specific surface area. However, the ERDT pattern is different. So therefore, the bulk structure is the same. Specific surface area is almost the same, but the pattern is different. That means surface structure is reflected in this ERDT pattern. For anatase, the CBB position, this is almost the same. For rutile sample, the CBB position is also almost the same. So that means the CBB position reflects the bulk structure. And depending on the content of anatase and rutile, the CBB position is changing. And also, at the same time, the ERDT pattern is different. So therefore, it is possible to say that the specific surface area without using specific surface area data or crystalline content data from XRD are not necessary to see the structural characteristics of those samples. And this is only the part of example of titania samples, commercial titania samples. And as you see, the ERDT CBB pattern are completely different with each other depending on the kind of samples. So that means this can be used as a fingerprint of titaniums, including macroscopic measure of surface and bulk structure as CBB and size as total density. So at least we need to know the information of solid, of bulk structure, bulk or surface size, and surface structure. By determining all these properties, it is possible to identify the solid materials. And the ERDT pattern reflects the surface structure. It is impossible to say what is the real surface structure only by seeing ERDT. But actually, ERDT pattern they reflect the surface structure. And the CBB position reflect the bulk structure, and the TD, that is almost proportional to the specific surface area, means the TD reflect the bulk or surface size. So therefore, the ERDT CBB pattern reflects all the required structures. So that is the one important point. So then, the other samples, for example, for the other kind of metal oxide, we cannot check all the metal oxides because there are so many samples. But this is the representative metal oxide results. Zinc oxide, strontium titanate, molybdenum oxide, indium oxide, bismuth oxide, tungsten oxide, and ceria. And all these metal oxide powders show those ERDT CBB pattern, depending strongly different depending on the kind of bulk structure. However, as you see in titania, even if the bulk structure is the same, if the particle size or surface structure is different, the pattern shape is completely different. And at present, we have no the absolute electron trap density for the metal oxide other than titanium, because we have the literature data of total electron trap density for titanium, but for the others, it is necessary to determine. However, even without, even using the relative density, it is possible to check the similarity of a differentness of samples. And this is the results of film, anodic titanium film. That is the anodization of titanium metal plate gives such a titanium nanotube. And actually, so many papers reported those titanium nanotube, anodic titanium nanotubes, but actually the characterization is very difficult, and they are almost amorphous and no XRD peak, and no other analytical data shows the structure. Only the SEM, scanning electron microscopic image, shows the difference of structure. However, it is possible to say that almost no other data. And by using this technique, the thinner film, this is 3 or 2 micrometer, but actually the density is very low. So, sorry. No, sorry. But the thicker film shows the ERDT CBB pattern. And actually, the different preparation method gives the different ERDT pattern. Especially, this peak might be due to the amorphous titania, and this part is anatase. And this part is a bit different amorphous structure. Actually, we are now trying to understand what the meaning of this ERDT pattern. However, this is the only one example of characterization of anodic titanium nanotubes. And as I said before, the amorphous can be detected also. This is the results of niobia, niobium oxide, Nb2O5. And the 6 patterns, the samples are completely amorphous. That means no XRD peaks, no characterization could be. But by using this technique, the ERDT patterns available as same as crystalline material. And actually, the surface structure is not so different, even if the bulk structure is crystalline or amorphous. And this left two sample is the starting material. And they are different. Probably they are not the niobium oxide. That is niobic acid or amorphous niobia. And therefore, the patterns are different. However, by calcination of higher temperature in air gives the similar patterns. So that means that the starting materials are different, but actually they gives a similar pattern that might be amorphous niobia. And higher temperature gives the different peak position. And this is also the amorphous niobia material. And actually no characterization is available by using XRD. However, this is a bit similar to this sample. So that is heated very, very high temperature. So probably they are similar materials. And this is a titania. For European countries, the people use this Cristal Millennium active PC series titania. And this code number reflects the specific surface area. The larger the number, the higher the specific surface area. And actually, the XRD shows this is anatics. And we believe that they are the similar anatics particle with different particle size. However, it is clearly seen that between PC 50 and 100, the peak position is completely different. So that means they are similar with different specific surface area, and they are similar with different specific surface area. However, actually, these two, PC 50 and 100, is a bit different in surface structure. So therefore, this is these two are analogous. These two are analogous, but there is some gap between this. So this is the only one possible technique to characterize or to see the differentness of these materials. And this is the results of titania, transparent titania thin film with thickness about 500 nanometer or thicker. And they are prepared in different technique with the same precursor. And this is these patterns, these samples are provided by private company, and it is impossible to open what is that. But actually, this is titania, is prepared in different way. And clearly, the peak position is and the shape is completely different depending on the kind. And in this case, the titania is totally amorphous, no crystalline phase. But this is possible. It is possible to check the difference by using this technique. Again, this is the only one possible technique to check the differentness of structure. And the wide bandgap semiconductor or insulator also gives the ERDT CBB pattern. For example, lanthanum oxide, that is very high energy peak, about 5 electron volt. And for tantalum, that is higher than 3.5 or 3.7. And antimony oxide also shows. And zirconia, this is not the semiconductor, that is insulator. And pure zirconia, silica, or alumina don't give the ERDT pattern, but the contaminated or doped material gives the ERDT CBB pattern. And actually, that is, how to say, not depends on the specific surface area. Of course, those detected electron traps are located on the surface, but this may not have the constant surface density. And for tin oxide, that is a bit complicated structure, but this gives the complicated surface structure of tin oxide. And not limited to metal oxide, carbon nitride, that is also the semiconducting material, those samples can be characterized. This is the XRD pattern of carbon nitride prepared from different precursor, those precursors. And XRD pattern doesn't give any important information of the structure because the bulk structure is not so different. Probably those heteroatoms, oxygen, nitrogen, or sulfur may be located on the surface. So therefore, the XRD doesn't give any information. However, by using this technique, the C3N4 prepared from different precursor gives completely different ERDT CBB pattern. And several features are by using the oxygen containing precursor, the CBB portion is a bit higher. That means band gap is a bit become wider. And the oxygen might be doped on the surface to give the lower energy peak. Still, we cannot assign what is that, but actually we can see the low energy peak by when we use oxygen containing precursor. And if the standard carbon nitride is prepared in air, a bit that the tailing at the lower energy part, similar to this oxygen containing precursor, is observed. That means oxygen in the atmosphere may give some oxygen doping. And the sulfur gives more lower energy peak. So probably we don't think that this is directly shows the sulfur itself, but the sulfur, the atoms in precursors may give those lower energy electron traps. Actually, it is possible to differentiate, and some information showing the correlation with photocatalytic activity is also seen. So then another technique is to check the similarity of samples. And this is the results of titanium, commercial titanium sample. And the sampling is made very, very carefully from the same bottle, in the same position, in the same bottle. So as you see, the ERDT pattern is almost the same. And we check the similarity of those samples by checking 3 points. One is this pattern shape, not absolute value. This is the shape of this curve. And the total density here, this is compared. And also CBB position. And all these degree of coincidence are calculated to be the value between 0 and 1. 1 is almost the same. The 0 means completely different. And by multiplying those 3 degrees of coincidence, the total degree of coincidence is calculated by using this equation, by putting some weight, light weight and heavy weight, and depending on the standard deviation of those data. And actually, for those 3 samples, the 3 pairs of samples gives this degree of coincidence about 0.9. And as you know, the sampling is made from the almost the same position in the same bottle. Therefore, the degree of coincidence about 0.9 gives it is possible to say those samples are same. But if we take the sample from a bit different position, clearly the shape is a bit different. And the zeta value is a bit lower compared with the others. So that means in 0.9, value of 0.9 is decreased to be 0.7 or 8. So therefore, this technique is very sensitive, especially for the difference in surface structure. So therefore, even if the same bottle of sample or titania or photoacoustic material, some heterogeneity are there. So therefore, we neglect those differences, but actually this technique shows clearly that such difference. And for titania, commercial titania samples, we checked all the pairs of samples by calculating the degree of coincidence. And actually, the zeta value is very low. Almost all the pairs show the very low degree of coincidence. This is natural because they are different titania, so therefore they are different. However, some pairs of samples gives a very high degree of coincidence. So this is the top 7 list of high degree of coincidence. The highest one is 0.788. And actually, those solid square, those solid lines say that the TiO4 and P25, TiO8 and ST01, TiO11 and FP6, they are the same with different, provided from the company or society with different code name, but actually the starting material is the same. And actually they say that the high data value. And the important point is this WACO sample. WACO sample is similar to TiO4 and also similar to P25. And the TiO4 and the P25 the same. So therefore, the WACO provide the titanium sample by putting their own code name, but that is just a P25. But the important point is these TiO4 and WACO shows the very similar photocatalytic activity. This value is the average of 3 photocatalytic reactions. So 1 means the same, 0 means completely different. And this pair, TiO4 and WACO, shows almost the same photocatalytic activity in 3 kinds of photocatalytic reactions. So therefore, even if this is P25, WACO provided P25 as their own product, but actually they can be the same. And therefore, the activity is completely the same. So that is the important point. So without seeing the code name, so only by checking the ERDT CBB pattern, it is possible to say they are different or similar or almost identical. And the extension of this concept is shown here. This is the degree of coincidence of titanium, commercial titanium samples. And this is the degree of coincidence of 3 kinds of photocatalytic reaction. And 1 means almost the same photocatalytic activity. But this is not the absolute photocatalytic activity, just comparing 2 titanium samples. And actually, there is almost no relation between zeta and zeta PC. So the photocatalytic activity is completely different. However, here is a line. So that means the high degree of coincidence of samples doesn't give the lower degree of coincidence of photocatalytic activity. So that means similar titania shows similar photocatalytic activity. By taking the moving average, this is replotted like this. If the zeta value is lower than 0.6, the zeta PC value is completely different depending on something like this. So so scattered. However, if the zeta value is higher than 0.6, this is increasing. And if the zeta value is of 0.9 or something, the zeta PC is almost 1. So that means the similar titania gives similar photocatalytic activity. And when we submit the paper, the referee commented that that is natural. Of course, that is natural. The similar photocatalyst must show the similar photocatalytic activity. Yes, yes. So that means zeta shows clearly and adequately the similarity of samples. And here, this is plotted for photocatalytic activity. So any kinds of activity, property, or something gives a similar plot. And we call this elephant plot. So an important point is same ERDT CBB pattern means same property and activities because they are same. And the different property or activities are obtained, they must show different ERDT CBB patterns because if they are same, then this must be the same. So it is possible to check the similarity, and by checking this, we can discuss the property of activity depends on the structure. The other important point is related to the photocatalysis. So there is no guarantee. Similar activity doesn't give the similar ERDT CBB pattern.
Hát már idősebb mosógépünk van, és valószínűleg ott a motor probléma.
Imre megy
Hát,
megy a mikrofonon.
Tudom a dobot forgatni. Amikor elindul a mosógép, akkor kattog, hallom a kattanást, hogy váltanást.
Imre megy a mikrofonod. Imre.
És nem tudom, hogy most a kefe, vagy égszív, vagy valamit tönkrementett. És azt szeretném kérdezni, meg tudják-e nézni, illetve...
Sorry, professor, I think, okay.
Sorry. So then we check the patterns depending on the photocatalytic activity in three kinds of photocatalytic reactions. Methanol dehydrogenation to give hydrogen, and acetic acid decomposition to give carbon dioxide, and oxygen evolution from silver sulfate solution. And the pattern is plotted in the order of photocatalytic activity. The relative activity 100, the highest to decreasing, and the lowest one is here. And for carbon dioxide and for oxygen evolution reactions. And as you see, that the pattern is not depending on the photocatalytic activity. Of course, the similar photocatalytic activity doesn't mean the similar ERDT CBB pattern. And however, for the carbon dioxide and oxygen evolution case, the higher photocatalytic activity sample, the higher the relative activity higher than 70 shows the similar ERDT CBB pattern. But middle or low photocatalytic activity sample doesn't give the similarity with each other. That means that for carbon dioxide and oxygen evolution case, the structure is almost optimized if the prepared in the similar method. And so, but for middle or low photocatalytic activity samples, the reason of this lower activity is different depending on the samples. So, for example, one sample is showed for low activity due to the, for example, low specific surface area, but the others gives the low photocatalytic activity because of the enhanced recombination of something with different structure. But the all higher activity sample gives the similar pattern means they are almost optimized. That means it is a bit difficult to expect the more higher photocatalyst in the conventional preparation method. However, for hydrogen evolution case, there are no similarity for high activity samples. So therefore, it is possible to optimize the structure of photocatalyst to give the much more higher photocatalytic activity. So therefore, this ERDT CBB pattern provides a new way of discussion of photocatalytic activity structure correlation. So okay, so that's the brief introduction of our technique for the solid sample, especially semiconductors. And applicability, application of this technique is not limited to metal oxide, but we have not so many, how to say, chance to check, to measure the different, many kinds of different samples. So therefore, we are very happy to accept any samples, and there is no guarantee. Every sample must show the ERDT CBB pattern, but they try to do. We are happy to try to measure the samples, and if that is measurable, applicable, that is very happy. So if you have any question, I'm very happy to answer.
Professor Ohtani, thank you very much for your talk, and
You're welcome.
yeah, I'm sorry for my late. Yeah, I have. It's really interesting, and we have a sample. So that's what I want to. Can I share my screen? Can I show just? Or maybe
yes, yes,
okay,
please.
thank you. So we are. Can you see my screen now? So
Yes.
So we find that so we are using manganese oxide as a support, and
Yes.
then we put platinum on the surface, and then we found that in CO2 hydrogenation we have a really big increment in catalytic activity, and
I
then
see.
And then we have all the characterization, you know, the TM images. We have in situ XPS, we have in situ TM now, we have in situ IR. So we know somehow what is the mechanism. And
yes.
then also we have, so somehow, you know, we always think that everything is going on the interface. And then, you know, this, can you see these TM images? You see that, so this is manganese oxide, this is platinum. And
Yes.
then somehow this is the interface, and then somehow it looks like there's a row missing structure, and also there is some, so there is some changes happening because the platinum manganese oxide interface. So
yes.
do you think that if we send you a sample of manganese oxide and one with platinum manganese oxide,
okay.
we can...
So
I'm
the
sorry,
only,
it was
okay.
I'm sorry, I get into
okay.
the deep, but
okay,
I'm sorry, I just wanted to be straightforward, yeah.
Honestly speaking, there are two problems. The one is that we check the change of photoabsorption by filling up electron. If the manganese oxide has electron trap, the manganese oxide might be black sample, dark colored. So therefore, before starting measurement, already some photoabsorption in the range of visible light. So therefore, the small change of photoabsorption is a bit difficult to detect. For titania or the other metal oxide, for example, we use the detection light of wavelengths about 625, the red light, and they have originally no red light absorption. So therefore, even if the absorption change is small, that is very, very sensitively detected. So this is one point. The other point is to accumulate electron in electron traps, we use methanol as a hole scavenger. So excitation of electron in valence band directly into electron trap, and the positive hole remain in valence band. And if this is remaining, the electron must go back. So therefore, we need to remove this positive hole by using methanol. So that means the electron donors are necessary to in this measurement. And if the platinum is there, the electron is moved to platinum. And in this atmosphere, the hydrogen is produced on the surface of platinum. So therefore, the electron cannot be filled up. So all the excited electrons are used for hydrogen evolution. So actually, if the titania is loaded with small amount of platinum, almost no peak appears. So that means all the electron trap, even if that electron trap is filled with electron, that electron is not accumulated, that is moved to platinum efficiently to give hydrogen. So there are two points. And another important point is manganese oxide might be P-type semiconductor. And actually, we have for the experience to check the P-type semiconductor, such like nickel oxide, NiO. And this is categorized into the P-type semiconductor. And actually, it is a bit difficult to see the peak. However, the important point is we can check this. And we have, for the first point, the photoabsorption is there for the detection light. But we have another LED in near infrared, 950. Sometimes the material doesn't have absorption at this infrared region. So in that case, if the electron trap gives the absorption in this range, it is possible to detect. So I cannot say that must give the peak and pattern, but we can try that. So if you have sample, please send us. We can try to measure.
Thank you for the willingness. So maybe if we decrease the number of the platinum, so we usually use 1%, but maybe just for this measurement, we really increase it to 0.1. Maybe that can help to avoid forming too much hydrogen, and then, but maybe we will see that how the platinum do the shifting of the bond.
So the most practical way of trial is please send the few samples. One is without platinum, low loading and high loading, if it is applicable, possible. So we can measure first the no PD sample, platinum deposited sample first, and if there is some peak, it is then we check the platinum loaded samples.
Okay. I still have questions, but I just wanna let others do.
Okay. Yes.
Okay. Thank you.
Welcome. Any other question?
I would like to thank you, Bunsho, for your talk. And I would like to know just a simple, I want to do just a simple question. Did you test nitrogen doped titanias or doped with metals or other species or other non-metal species? Are you interested in that kind of sample?
Yes. We have no experience of such a doped nitrogen or sulfur doped materials. Actually, I think that those doped material gives a different pattern depending on the kind of dopant and also the concentration. And it is not so straightforward. So actually, we can observe only the pattern, shape only. And there is no structural information. What does it mean? And we need several or many samples, different samples. And by checking and by comparing with the other conventional analytical data, it is possible to say something from this ERDT pattern analysis. So I recommend to send us the few samples with completely different characteristics or property or activity. And different activity or different property sample must show the different pattern. And by checking the, by analyzing, by discussing the difference of in the other analytical method or activity or property, I think it's possible to say what does it mean, those ERDT pattern, position and pattern shape. Hi.
Okay. I have to leave because I have to move towards my workplace, and
Hi.
I am very happy. I will see again the registration, and I hope to send some interesting samples.
Yes.
For practical reasons, how many samples do you prefer to receive, for example?
Actually, any sample is okay. So at the present, we have 5 instruments with almost the same, power. And we accept many samples from the people in university and also private companies. But actually, it is possible to check that. Sometimes it needs, for example, more than 2 weeks or something, but actually we can accept and adjust the measurement time for your sample.
Okay. Thank you again, and I would like to.
I will give the my email address in chat. Please check. So please send me the email if when you send the samples for me, and I will tell you the address of sending your samples. Can you see the chat? Ohtani at cat.hokudai.acjp. Or in the program of that NPT, you may find my email address. Or just checking the internet, I think it's possible to electron draft distribution analysis gives some articles. Hi.
Hi, Professor Ohtani. I'm
yes.
Sorry I couldn't arrive.
No problem. No problem.
I missed your talk.
Sorry.
Have you recorded the?
Yes, now this is
Okay.
recorded. So I will give you the URL for this
Okay, thank you.
movie.
Thank you very much. I have some samples based on titanium dioxide with silver.
Yeah.
So I miss your previous talk. So I understood that maybe it's not a good material to analyze for the metal particles.
Actually, silver might give some interference of the measurement. However, you may have the sample without silver, and by comparing the results of sample with and without silver or different silver content, that may give some structural information of your sample.
Okay. So the ideal materials that you wanted to, to obtain good results should be which one? Because I have many options.
Yeah,
So
yeah.
what is
Actually,
the ideal?
okay. Actually, the titania itself gives surely the ERDT CBV pattern, so it is possible to check. And the important point is you may want to see the difference of sample. What is the difference between the samples of different activity or performance or something? And it is sure that different activity sample gives different pattern. And by gathering the accumulating all many results with different property or activity and with different ERDT CBV pattern, it is possible. I think it's possible to understand what is the real true difference of structure of samples, giving the different particular activity or the other performance.
And what is the main difference between this technique and, for example, photoluminescence?
Actually, photoluminescence is a very sensitive technique. However, that is detected only luminescent material.
Okay.
But this is really the macros. The part of result reflect the macroscopic surface structure. So therefore, any difference in surface structure gives a different pattern if originally the sample gives the patterns.
Okay. Okay.
So anyway, please do not hesitate. Any sample is okay, and a completely different property, different activity sample, few or several samples, please send us. That we can check and we can see the difference. And by discussing online, it is possible to make further experiment or further, the modification of measurement technique. Sometimes we, for example, if the material contains organic residue on the surface, sometimes the electron traps are, covered with those material and not so many and not so much peaks. However, by the ozone treatment before measurement, such electron trap are sometimes recovered. So by checking the difference of patterns before and after ozone treatment, there is some information about what is, the contaminated. Sometimes the surface structure is much contaminated, but in the ordinary analytical method doesn't give any information of such a surface modification or surface deposition. And also the important point is the amorphous structure. we didn't check any amorphous structure on the surface, but this is very sensitive. And even if only the surface structure, surface few layers are amorphized during the preparation or modification process, it is detected. In the ordinary XRD doesn't give any difference.
And for example, if you have a combination between titanium dioxide and an adsorbent, so maybe this could modify the bottom-up, could be tested or could be very difficult?
Yeah, and any sample can be. So please do not hesitate. So please send us samples and we measure. And if that is not detected, that is also the information. And if that is detected, that is very happy to proceed the other samples.
Mm-hmm. And the amount of the sample?
Yeah, for powder, we prefer to accept the sample about 300 milligram. But 100 milligram is the minimum. But it is a bit difficult to check the reproducibility.
Okay, 300 milligrams. Okay.
Yes.
So thank you very much. It's very good to see you.
So any other questions?
Professor Ohtani,
yes.
Thank you for presentation. And I have one question. I found that most of your samples have band gap around 3 electron volt.
Yes.
And the modulated light wavelength is 625 nanometers. Yes. So can we test the samples with band gap, narrow band gap, like around 2 electron volt, and can the wavelength of the modulated light be changed?
Yes, it is possible. So as I told before, that is we normally use 600, but we have another setup, 900, and more longer wavelengths, near infrared LED is also available. However, the 2 points. One is the electron trap, field electron trap must show the photoabsorption in this longer wavelength region. So, but it is possible to check that. And the lower, narrower band gap one is the narrowest one for our experience is tungsten oxide, 2.24 or 2.5 electron volt. That is okay. So very, very good patterns are obtained for such material. But actually, the important point is sometimes the narrow band gap semiconductor is P-type semiconductor.
Yes.
So P-type is a bit difficult. So actually, in our experience, it is not possible to check such a P-type semiconductor. P-type semiconductor doesn't give peaks in this measurement. But actually, we don't know the real reason. So therefore, that might depend on the sample. Something that the other sample may give. So please do not hesitate to send the sample, even if that is P-type semiconductor.
Okay, thank you.
Professor, do you have a chance? So usually before we use our samples, we do a heat treatment that in oxygen and hydrogen.
Yes.
And then is it possible if we send the sample and then maybe you do this pre-treatment on the samples?
Yes, of course. And that might give the, how to say, the difference. And if you are prepared in the inert atmosphere and you need to keep in those atmosphere, please seal in the vacuum sealed package, and we can open the sample in grow box to be set in photoacoustic cell. So therefore, even if you need to keep the atmosphere before the measurement, it is possible.
Okay, okay. So, and 300 milligrams is from one sample, yes, as I understand.
Yes. So at least a few samples should be sent, because only one sample doesn't give any, how to say, information. So we needed to, yeah, that's right. And for example, if that is deposited on the surface, so the adsorbent, so that is the base material should be checked.
Okay, perfect.
So
we just published a paper where we had bulk cobalt oxide, and then we produced another cobalt oxide based on a mesoporous technique. So the surface area was almost 5 times higher than this.
Wow.
And then we found really nice differences in catalysis. And we believe that somehow the basic sites on the surface was different, and that's how the catalytic activity was all again. So do you think it's possible somehow to connect your measurements with the structure and maybe with basicity or with other catalytic,
I think yes. In general. So that is the basicity of acidity of sample, solid sample, must be originated from the surface structure. The surface structure different must be reflected in ERDT pattern. So therefore, it is possible to check.
Okay. Thank you very much. It was really interesting. I'm really looking forward. Okay. Thank you.
So any other questions or comments? Okay. So now this meeting is closing, and I will send all the participants of NPT of the address of this meeting. This should be uploaded to YouTube. So thank you joining us. Thank you. So we are happy to waiting your sample, accepting your samples.
Thank you very much, and have a nice evening.
You're welcome.
Morning, or whatever.
Now it's 5 o'clock. 5 p.m. 5 p.m.
Okay. We are starting the day.
Yes. So bye.
Bye.
Thank you very much.
Thank you.